The last talk before the coffee break session will be given by George Smoot. George Smoot is a professor of physics at the University of California, Berkeley, a senior scientist at Lawrence Berkeley National Laboratory. George Smoot went to MIT, where he obtained a dual bachelor's degree in mathematics and physics in 1966 and a PhD in particle physics in 1970. He worked as a postdoc with Louis Alvarez at LBL, where his attention turned to cosmology, cosmic microwave background radiation. George Smoot did pioneering work to develop precision differential radiometers for a number of experimental efforts, culminating in his leadership role in NASA's Cosmic Background Explorer, the COBE experiment. I remember being at the University of Chicago as a young scientist and going to a special seminar by Mike Turner to announce the COBE results, and it was electrifying, breathtaking experience. For his critical role in every aspect of the COBE project, George Smoot, along with John Mather, won the 2016 Nobel Prize in Physics, and today George will talk to us about the cosmic microwave background. Please welcome George Smoot.
Thank you very much for the opportunity to talk here. I'm not going to talk about the cosmic background radiation because I try and be out of the way of the next generation, but it's going to come anyway because I'm going to talk about the future cosmology, and you can't do that without the cosmic microwave background too, but it allows me to be much more speculative and get into much more trouble. So here's a picture that I made to explain to people 25 years ago what the results might be. It's a pretty simple view of how you get the universe from nothing, or practically nothing. But we've made some progress since then. So here's kind of the current day example of comparing the energy density in matter and the energy density in dark energy, or Planck constant. And you can see there is concordance between the cosmic microwave background, the supernova, showing the accelerating universe, clusters, and also baryonic acoustic oscillations. That is the sound waves in the early universe producing the things that Rocky was telling you about in the fits. And so you can see we've got a situation where combining measurements, we're able to get things fairly precise. The CM measurements can often be more precise, but when they're added to some large-scale structure data, you can get things quite a bit more precisely. And so far, everything is fitting into what we call, in shorthand, lambda CDM, or a dark energy, cold dark matter model, although people always are looking around the edge for things that are frayed. Okay, and this is a thing that Rocky showed to you so he could be a little chemist, but the thing that we talk about most of the time in the standard model is the little colored section up there, and it's a small part of what we think is important in the universe, and Rocky was more diplomatic about saying where the standard model is falling apart than I probably will be. But it's interesting to note we have these other elements that are critical to our understanding of how the universe got to its present state. Okay, and we have a standard model which we work out from the time I was a student. We had the Robertson-Walker. We assume the cosmological principle. You get the Friedmann-Lemaitre-Robertson-Walker metric. You assume this for perfect fluid. You get the Friedmann equations, and you solve them. That's cosmology. Well, it's getting a little trickier than that now, but that's basically what we still do. And here's a picture that shows a little, that we made up sort of more recently. Here's the data that came to 25 years ago, showing that it's the radiation from the beginning of the universe, showing that the universe is very isotropic on a large scale, and that there are these cosmological fluctuations that are at the 10 to the minus 5 level. So it's the Robertson-Walker metric with perturbations at 10 to the minus 5 level. That makes it easy to do perturbation theory, although you see people don't do it. But you can also realize there are more epochs that happen in the universe, and I'll come back to that later on, because that's one of the ways the cosmology and the standard model fit together and work on things. Okay, so here's an example of some data. This is the angular power spectrum, and sorry, it doesn't label that way. The angular power spectrum, and you can see now, you see spectral lines. They're very broad lines, but you see spectral lines, and you can count peaks, and you can see the data, and you can see also the E-mode calibrations and so forth. And we take these data, and we start with an intensity map. We assume isotropy on the sky and collapse that down to one dimension from two. measure the angular power spectrum, and then fit to the cosmological parameters. And you can see, except this is distorted, you can see that over time, we've been narrowing the error bars down significantly, so that many things are down at the 1% or slightly smaller level these days. So we're making progress, and this reminds me of the early days of the standard model, when there was a standard model and the error bars were a few percent, and then they were 1%, and then they were 0.1%. So that's the kind of thing that's going on. Okay, so up till now, the observations are showing a very good fit to the cosmology model. The CMB map on the left, next to it, a relatively nearby galaxy map. You fit that galaxy map and make a power spectrum, a matter power spectrum. You see it going up, and then you see the baryon acoustic oscillation wiggles showing up just as predicted. So everything is fitting together, that you have this fluid, it's expanding, the universe has got some oscillations, there's the decoupling, things form, and everything goes out. And those are just examples. So now I can start predicting the future. Right? It's easy to predict the next few years. It's much harder to predict further on, right? And the reason is experiments are starting to get big in cosmology the way they have in particle physics, so you can predict what experiments are coming. So I'm going to talk about the galaxy surveys. So the next is the DAISY survey. The first was the Sloan Digital, well, the first one I showed you, Sloan Digital Sky Survey. It went to Sloan Digital Sky Survey 3, or Baryon Acoustic Oscillation Sky Survey, BOSS. And the next one that will be starting up next year is DAISY. And you can see the volumes being done, but also the scale at which we're going, where you're talking about 10 million galaxies, 4 million galaxies, 17 million galaxies, 2.4 million QSOs. And you look over here on our Moore's Law diagram, time versus the number of galaxies you're surveying, and you can see it's a nice straight line. And going from 1 million to 3 million to 30 million and so forth along the way. That's the scale at which these experiments are going on. So that's what you can predict. That's where we're going to be in 5 to 7 years. We're going to have maps that are going to have 30 million galaxies in it, including the quasars and other things. And it's a steady improvement. And you can do the same sort of thing for the cosmic microwave background. So Douglas Scott and I periodically produce a review of what's going on. And on the left of the theory of what the scalar perturbations should look like, based on that simple model, you can then predict what the power spectrum of the temperature fluctuation should be, the temperature E-mode polarization cross power spectrum, the E-mode power spectrum, and the B modes from the lensing of the large sieve. And that's all simply based from those other fits, and that's all so forth. And then you can say, well, what about tensor modes? That is, things that will turn into gravity waves when they come inside the horizon. And we put there, at a scale a tenth the level, what that spectrum should look like. And what you see on the right is we've got nobody in tensors, but we have extremely good measurements already for the scalar power spectrum. You can see the temperature power spectrum on the top. You can see the E modes, the cross TE is not shown here, and the lensing B modes. This is the status of their measurement to now. And you can see these are really impressive measurements. I mean, 25 years ago, I thought it would take longer, right? But we're here, right? And now we have, this is from the CMB S4 forecast, which is the stage 4, and here are predictions of what the error bars will look like in the future. So let me talk about those experiments. Okay, so first of all, the stage 4 ground-based cosmic microwave experiments, CMB S4, are particularly, I'll show you, from the South Pole and the High Chilean Atacama Desert, two places I went to early and had experiences there. They got it easier now. There's places to stay and stuff. And but you can also see here a plot of the year and the approximate sensitivity of the experiments. Again, it's a kind of a Moore's law, except it's quantized because you only do the experiments in quantized middle. You can see the sensitivity improving incredibly. And basically, for the last 7 or 8 years, we've been near the quantum limit, and the way the sensitivities improve is simply adding more detectors. Right? We're not quite to the quantum limit, but the fact is it's a lot easier to add detectors than it is to try and get that last little bit out. So again, I can predict this part of cosmology for the next few years fairly well. All right, so here's the scale, 2015 to 2023. There's the stage 2, which is already run and essentially finished. There's stage 3, which is going on now. There's a stage 3.5 that isn't quite shown in here, and the stage 4. And there it says 500,000 detectors. It's really going to be over 1 million detectors, but we'll see what's going on. And this map on the right is the Planck map at 353 gigahertz of what the dust looks like from the galaxy, telling you where you want to look in the sky in order to see that. And you can see you're going to do improvements because your sensitivity is going to improve. You're going to get a limit on the tensor modes, which allows you to put limits on inflation and a number of other things. You can put a limit on the sum of the neutrino masses, and you could do tests of the dark energy, something that we didn't think at the beginning was going to be important, that the CMB couldn't really do, but in fact the CMB is playing a big role in that also. So here is the example of the 2 cities that CMB built, right? One at the South Pole, right? The South Pole telescope, 10 meters. Chicago has a big role in that. Rocky. See, I get it. I get $10. There's the BICEP and the Keck and the upgraded BICEP decays that are down there. Some of you might remember these guys made a lot of noise about 2 years ago. They're still getting ready to make noise. We're going to see what's going to happen. And this is up in the Atacama Desert, which is where the stage 3 activities are already starting, and there are these various detectors, and the infrastructure has been put in quite a lot. So you might ask, why are they there? And the answer is because those are the good sites where you can do it from the ground. There are 4 sites from which you could hope to make CMB measurements from the ground. One is at the South Pole, and the reason for it is water vapor. The atmosphere creates noise, but water vapor is very variable, so you have to go to a place where the precipitable water vapor is very low. The South Pole is extremely good at that. That's why it's shown here in blue. The rain shadow of big mountain ranges, especially if you can be on another mountain range right behind it, that's also a place that's high and dry. And so the Atacama Desert, that is not on the main Andes, just one set in, is another one. This is plateau in Tibet behind the Himalayas, and on Greenland. Those are the 4 places on the Earth from which you can hope to make the measurements. Okay, so what you can see is there's a big effort in Antarctica. That's a place from which you can make good measurements, but you're limited in how much sky you can cover, but you can do deep surveys there. The Atacama Desert, you can cover a lot more sky, but you can't cover the whole north sky. You can cover the middle part of the sky, plus you have to avoid the galaxy, so there's another issue there. So the next thing that's happening is there's going to be a site just behind in the rain shadow of the Himalayas. It's called ALI CPT. It's ALI Cosmic Microwave Background Polarization Telescope, right? That's what ALI is the little region there. And it's up in a high altitude behind the Himalaya Mountains. So most of you haven't heard of this, so I thought I would spend a little time on it. Okay, here is the ALI CMB program observing site, or sites. ALI CPT-1 is supposed to begin operations in next year with 7,000 detectors. That actually pops them into sort of the same scale that's going on at the other places. And by 2020 to 2022, the second site will be added with a second telescope at approximately 6,000 meter with more than 20,000 detectors in it. That's sort of keeping it sort of on a comparable level to the other ones. They're slightly behind, but they're making up for it. And so in the upper right-hand corner is a picture of the experimental shack that's being built there. It's nearby where China has these large telescopes. It's the next little peek over. And here's the ceremony. So you can actually see the Himalayas behind, so you can tell you're in the range. Look how dry it is here, and look how much snow there is on the other side. So that's telling you it's doing the right kind of thing. And here's the kind of sky coverage you can see superimposed upon the Planck, our Planck measurements of the dust, but the dust polarization, right? Because that was the issue for the BICEP Keck. And so you can see from the South Pole, you can do a lot along the bottom. There's some good windows you can see from the South Pole where it's sort of blue. From the desert, you can see a bigger, broader section, but from Ollie, you can see an even broader part of the sky. You can get all the way to the top and down below the equator, so there's big overlap between the two. And here are if you just look at the dust, here are the places where Ollie is planning to be making its surveys. So this is new, and we'll see how this goes, because these people are coming into a field that's very advanced, and they're trying to come right up to speed at the top. And so it'll be an interesting development of what's going on. So what I'm going to say is you can predict the big things that are going to go on in cosmology in terms of the surveys and in terms of the CMB observations. There's some other things you can predict about LSST and some other things like that. But basically, I think that the field is going to see steady advances over the next 5 to 7 years because of these big programs that are put in place. But if I had to bet, I'd probably take equal money on whether there's going to be a significant discovery or not, or whether we're just going to be tightening down on the model of cosmology and getting the parameters more and more precisely, right? But it's not that there isn't enough trouble. Okay, so now I want to go and speculate a little bit more and think about stuff. So I thought, well, if I'm going to talk about the future, I ought to think, what would the long-term future look like? Well, I wanted to be optimistic, so I said, why don't I postulate the Copernican time principle, right? And that is, there's nothing special about the current cosmological epoch, right? There's no special significance to being here now, even though there are lots of people arguing that we're living in a special time or a special place. And so in order for that to be interesting, that means physics processes will have to continue to take place in the future, in spite of the fact that we're going to see more and more decreased energy levels. And then I had a slide about how I wanted axions, and then I want axion-like particles, and I got to get 10 to the minus 18th EV, and 10 to the minus 22 EV, and 10 to the minus 28 EV to keep doing this stuff. But let's think about what we've learned about using symmetry in cosmology and using these kind of statements. How has it helped us? How has it hindered us? And how do we interpret things now? So, oh, sorry, I should show you some pictures. You know, depends on how you do it. You can divide this up. This is a slide from Fred Adams, who's worried about the long-term future of the universe. He divides it up into 5 areas. It's a feature of humans. They make the slides be something you can read in some reasonable short time period instead of having an infinite number of slices. I think that I can make up a thing where there's at least a major cosmological transition every 10 decades, and sometimes I can do it every 10 e-foldings, but that's kind of a thing. And so let me look at the most sacred symmetry that we had in cosmology and that I used since I was a child. You know, it's the cosmological principle. It's a symmetry principle that says the universe is homogeneous. Of course, you have to limit that to the larger scales. That there is isotropy. Doesn't matter which direction you look, everything looks the same. And universality, that the laws of physics are the same everywhere. Now, how does this hold up? Well, the answer is it fails locally. Here's the map of the distribution of galaxies. This is the Sloan Digital Sky Survey map of 1 million galaxies. Not quite all of them shown. But you can see it's not exactly homogeneous. It's actually got structure in it. But if you average on a big enough scale, maybe, right? So there's an element of truth in the cosmological principle, but it's not an element of rigidity. It's a broken symmetry. Okay, so here's the experimental data. On the bottom here is in log the scale in megaparsecs and the delta rho over rho. And what you can see is on the small scale, there's a lot of inhomogeneity, right? We know that. Look at this room. It's pretty inhomogeneous, right? Look at the Earth, right? And you can look at the radio, you can look at the X-rays, you can look at galaxies, you look at the CMB. When you get to the very large scale, and here we are at the scale, sort of the horizon size of the observable universe, it's really good. It's 10 to the minus 10, right? So that's a pretty good thing, right? And you do the same thing. You can do it in another scale. You can do it in galaxies. You can do it in weak lensing. You can do it in other things. It works out, that on the really big scale, it's kind of homogeneous and isotropic. But the question is, does that come from a principle? And the answer is no. We think it comes from a dynamic process. That we got a symmetry because we had a dynamic process that's put us there. Originally, we thought it was initial conditions. Now we think there's a dynamic process that happens in the universe that gives us that situation, right? And this is the example I took from Alan Guth because he had a nice, pretty figure in it and so forth. But we believe that we have an early de Sitter phase to the universe, and that gets us into a situation in which we get pushed towards a flat universe and a universe that has perturbations that are, in this case, 10 to the minus 5 in RMS, or 10 to the minus 10 in power, and it explains a lot about what we're seeing. And that also means that if you look on a big enough scale, that thing's going to turn back around because we're going to get outside of the inflation horizon, and you're going to start seeing the dragons or whatever's out there, right? Or you've got to put more inflation steps in there. It's hard to go past 50 or 70 e-foldings. It's a tricky thing. So I got all excited when I heard about the early gravity wave binary black hole mergings, and I thought it's pretty amazing. This is good motivation that the black holes could be the primordial dark matter. And I spent a bunch of time studying that with a postdoc, Razi Imami, and what I concluded was the primordial black holes must be less than a few percent of the dark matter, so it gets less interesting. But I also found two other factors that had to be in there for them to become the things for the LIGO. And so I got less interested in black holes and set the limits and got out of there. But I thought, well, we've done all this work. Let's turn on a paper that says, what are the limits of the primordial curvature spectrum, right? What's there? And so the CMB and large-scale structure, they give us the limits down here at the few 10 to the minus 10 level. That's the CMB and large-scale structure in Lyman alpha. And then the CMB spectrum gives us limits. And then if there are WIMPs or other kinds of things that could be failed black holes, you get limits. And then it's just black holes that give you the limits. And so you got a large distance you can't go, right? But let's think about what actually happens in our ideas in the standard model of what appears in there. Well, I drew this in by hand, that's why it looks rough. We know that we waste a lot of potential, right? So that by the time we're in a megaparsec or something, we're actually down a factor of 10, so I didn't draw it coming down fast enough. But at some point, we get supermassive black holes. And roughly, it's a little tricky here, but the power spectrum is such that you get these black holes that are between 10 to the 6th and 10 to the 10th solar masses, and they have about 10 to the minus 6th of the material in the galaxy stuck into these black holes. Now, how does it work out like that? That you went out for something that's probably very limited till you get that? Well, there's more things that happen. You get Earths, you get stars, you get stuff like that on this kind of a scale, and you get atoms and you get nuclei. So what are these, right? The nuclei is the strong force shielding itself, right? The atoms are the electromagnetic forces shielding themselves. That is, they're neutralizing the current, the charges. And the only thing that doesn't have a neutralized charge is gravity. It's the one that causes the problems and tears up the fabric of space-time. All these others are building blocks for everything else you make besides the black holes. Right? They're the input to the black holes. So what does this mean? Okay, well, back to me I'll show you some pictures. There's all these possibilities of things that were going on. This was just to convince you, I could make something happen at least, every 10 decades so that I couldn't live some special. But I think there is a limit on both ends to where you could go. So the cosmological principles are going to fail. And so I look at it, I see them all as broken symmetries, but broken symmetries that had some element of truth that helped us. In the early days, we couldn't make the cosmological model without the cosmological principle. But the Copernican principle is obviously a failed principle. It was just to set our minds right. I mean, the Earth is a pretty special place. Is it any other place that you think is okay within, say, 3.5 light years? The answer is clearly no, right? There's no planet B, right? There's not that many even in the local region of the universe. But so each one of these has failed in some way or another. The perfect cosmological principle, which is extremely beautiful, clearly is wrong, right? But it would have been a really beautiful theory. I'm setting you up for saying, don't get too wedded to symmetry principles, because we get our cosmological principle now, looking back, from a dynamic process. It arises spontaneously. It didn't come from a fundamental principle to begin with. It came from a process that went on. And the anthropic principle, I'll replace that with the standard model can only exist in a universe that exists the way it is now. And I'll go to an argument about that, and you guys can then fight back later on. Or you want the strong anthropic principle, which is a good standard model can only exist. The universe is made to make good standard models. So it's a different kind of a way of looking at things. Okay, so how do we get what we have now? Well, we use the Einstein-Hilbert action. We use a variational principle. That gives us locality and a boundary, and that boundary has all the information. It's kind of the holographic principle. All the information in gravity is held in the boundary as well as in the bulk. Okay? And you use the Lagrangian and you do this kind of stuff, and you add the Einstein-Hilbert to the standard model Lagrangian, and you derive it and you get the Einstein equation. Well, how would I do it differently? Well, I would look at the standard model, which we all agree is beautiful, except when you write it down, it's not as pretty, right? And say, you should be varying the matter component too, just the way you're varying the metric, if you're doing a geometrical one, or you're varying something else. You should be varying the Lagrangian components of the standard model, or not the standard model, just do it. So I would take a bunch of particles with zero mass and put them in. Maybe one where it's got a force which is m phi squared, going to produce inflation. I need a de Sitter thing at the beginning. I need a de Sitter thing at the end. That's in order to keep Gerard from screwing up quantum mechanics. If everything is always going out and no noise is leaking in, it's like Ohio. The beginning is round, the end is round, the middle is high, but you got to turn it around so that only stuff leaks in is stuff that was already resident in the universe and you already knew about it. You don't let the junk from really far away back in. So you've got to have de Sitter or de Sitter-like, a little bit of deceleration, and then de Sitter-like again. Otherwise, I can't have a standard model, because then I won't be able to make the theories actually work. And so so I claim you just start out and you put in some spin 0 particles, you put in some spin 1/2 particles, you spin in some spin 1 particles. I don't see any reason to do 1.5, but if you're really brave, you could do a spin 2, and then you wouldn't have to put the geometric one in. But that's a little bit. And now you go and you do an extremization of the Lagrangian, right? And we know how to do this. Feynman told us this in ancient times. You do the Feynman path integrals. You don't do the simple Lagrangian, you do the e to the IH Lagrangian, right? And you need a very good thing like this. You need the distant past, distant future. You need to guard those with de Sitter, and you need the horizons, and you need not bad information coming out of the horizon. You need only good information flowing out of the horizon. So you get partially conserved currents, but that's it. And you go and you try and do the extremum of the final Feynman path integrals. And I would predict, although I don't know for sure, using this prescription, you will come out with some symmetries emerging, probably SU3 and SU2 and SU1 and some U1s. It's an exercise for the students to do this. Okay? So what about, the super everything? This is a super everything institute. We do it superchargers, superclusters, supercolliders. What about supersymmetry? Well, super's cheap these days, but you probably can get supersymmetry if you work really hard. Depends on how you feel about this. Okay? But also, don't get too carried away with, symmetry. So here's the somebody you might recognize, saying, look how great things get when you go to 92 dimensions. Well, it's true, it's pretty. Remember the steady state theory, it's extremely beautiful, but also extremely wrong, right? And not so useful either. And, you know, these guys that aren't here can't defend themselves. You know, I was wrong about information theory. Well, maybe we need some information loss. We just need a little bit leaking out over the horizon and the black holes. That's just to keep the sign right, to keep the conserved currents from bringing in bad stuff, just having good stuff in the system. Okay, so the bad news is this goes against every grain in my body. You're gonna, you know, instead of having this simple thing where we have the primitive material, we get this inflation and the Big Bang and everything goes cool, right? And there's only one. You get the goddamn multiverse, right? And in my theory, this would be called ghosts or dragons or worse, right? It's a terrible thing. And so it hurts me to provide this prescription, but I think it's time for people who work on the standard model to not think, look how pretty it is. They should be thinking, what does it take to make a universe in which it would actually be right, which is going to require the de Sitter and the de Sitter. It's going to require a few other things. And when you're doing that, you might allow some other things in the system. So I'm almost on time. And remember, not only we have to make a universe where the standard model gets to live beautifully, we've got to reproduce this. So this is a recently released Gaia map, which shows like 500 million stars. You can see this is not trivial to make this. I mean, this requires a pretty complicated set of models. And so, you know, but you've got symmetries that kind of arise dynamically. There are going to be a number of symmetries if you use this kind of a Feynman path integral that will arise automatically from making a stringum of the Feynman path integrals. Those symmetries will arise in the standard model even without putting them in to begin with. So that's where I stop because I figure you guys are going to ask me hard questions now.
We do have time for a couple questions. Anybody?
Nobody wants to. Great.
No?
Oh, then you can go out and get pictures.
Yeah. Okay, oh, good.
You talk about the cosmological principle as a symmetry, but it could also be viewed that its original suggestion was observational, I thought. Oh, at least that's what somebody...
Yeah, we just didn't have enough data at the early days of cosmology to have an idea what the geometry and the topology of the universe was. And so people made the simplest possible conclusion. They said, we're going to take the maximally symmetric space. That metrically symmetric space gives us the Robertson-Walker metric. Then it's easy because we've now made a one-dimensional general relativity problem, which becomes a one-dimensional, you know, kind of an equation. And you can, the symmetry, it's just like you can do the black hole that's spherically symmetric is a lot easier than a torus or a wormhole or something. It's just a much easier thing to calculate. And people did that in the early days because there was no constraints on any serious way. In fact, if you looked in the early data, it seemed like there were a lot more galaxies in the north than there were in the south. It was not supported by the observational evidence, but there weren't very many surveys and there wasn't much data. It was the radio surveys that started to come in. But you have to remember the steady state model was still a viable model up until, I forget when, probably the 70s or something like that. Well, probably 64, something like that. But there were still arguments going on in the 65. That's the kind of thing. And so it is a kind of a thing. Now, we've all been raised to think that symmetry principles are extremely important. We like Emmy Norther really well. And so I'm just saying it's time to take the training wheels off the bike and see if we can do other things. Because in the case of cosmology, it's really been a few years we could have realized that the cosmological principle wasn't really a principle. It really was the consequences of a dynamic process, which you think is inflation, right? And if we go far enough, it will not be a correct principle. But it arose, and it looks very symmetric, and it's good to impart in 10 to the minus 5 in terms of metric perturbation theory, and 10 to the minus 10 in terms of power spectra, or 10 to the minus 10 to the minus 9. It is. It seems like it was right, and it was a good thing to do at the beginning. It was just a way to start going, right? To get going on the theory and be guided. But now we are in a position where we think a lot of these things should arise dynamically, and so we don't have that knowledge in how to do it in baryogenesis yet. But Rocky was giving you examples of different ways you could come up with schemes to do that. But there are other symmetries we see in the universe that we don't think are put in as symmetry principles. They have arisen because of the dynamics of what went on in the universe. And so I think the same thing could happen in the standard model.
Great. Let's thank George Smoot for that great talk.